yeah, what we've been doing. Okay, so let me do one more example. Maybe this will kind of nail your understanding. So here's an example. Show that omega equal to dz over 1 plus z squared extends to a holomorphic one form on projective line minus these 2 points plus minus I. Okay. So we want to show that this extends to projective line minus these 2 points. Of course, those 2 points, these are the zeros of 1 plus z squared, right? And there is no cure for those 2 points, and we are excluding. So the question is to extend it to infinity. So the only thing is extend it to infinity. So you have to show that this thing extends to infinity as a holomorphic one form. Okay. So how would you do that? How would you approach this? Because I mean, when you look at it, of course, infinity, you cannot go directly with infinity. You have to do something, right? We make a change of coordinates. Yes, exactly. So let W be equal to 1 over Z, right? Or Z equal to 1 over W. So let's see. So in other words, we bring infinity near 0 and then see what happens near 0 and then study the form over there. Maybe extendable, maybe not, right? So then omega becomes, okay, so Z is 1 over W is D of 1 over W over 1 plus 1 over W squared, right? So D of 1 over W is minus dW over W squared. And this is 1 plus 1 over W squared. So what is that? That's equal to negative dW over this cancels, get 1 plus W squared. So this is near 0. At infinity, it is of this form, where this one is near 0. Now, what happens if W is equal to 0? I mean, this has a limit as W goes to 0. This is nothing but dW, right? So this guy, this one form, dW over 1 plus W squared, of course, this approaches to dW minus dW. So this is extendable, and is in fact is holomorphic there, so this is fine. Okay. In other words, we can say that this function 1 over 1 plus W squared is holomorphic at 0, and this is also holomorphic one form, so this is holomorphic one form. Right? Okay, so I think we want now, so with this example, we are in good shape, so I can now talk about integration of one forms, just to recall, really. Any questions? Okay, so now let me just start this chapter, which is section rather integration of one forms. On Riemann surfaces. Okay, so now let's assume omega belongs to omega 1 of x is a one form, and I'm not assuming this one form is holomorphic or anti-holomorphic or anything. It's just a one form, right? And C from 0, 1 to x is a parameterized curve on x. Parameterized. If you want maybe piecewise smooth curve on C. So it doesn't have to be closed, it can be, we have a curve, so this is A, B, piecewise smooth curve connecting A to B. Obviously A is C of 0 and B is C of 1, and we want to define integral of omega over this curve C. So how we define this? You know how to integrate one forms over curves over in Rn, right? In n-dimensional spaces, for example, or in but we are over a Riemann surface. What would you do in this case? Right? So the idea is you just choose coordinate charts, the cover this by coordinate charts. Right? By finite number of coordinate charts, you can cover such that, okay, I mean, this is in the union of, so the idea is the following now. Pick coordinate charts. U1, U2, UN. I mean, coordinate domains inside X such that this C of 0, 1, the image of your curve is actually in the union of all these things, right? UI, I from 1 to N. Right?
UI is the image of the chart.
No. I mean, so for us, UI, these are already on the Riemann surface. It's the opposite. So I'm not.
Okay.
Yeah. Okay. So once you do that, then you can do the following. So what you can do, you can take points here. So then this implies that there exists a division, or I mean points. T1, T2, Tn less than 1, bigger than 0. I mean, you have to choose points such that there is T1, T2, Tn, such that, or maybe I just say this is equal to T0, and this is Tn minus 1, and this is equal to Tn, such that basically C of Ti, comma Ti plus 1, is inside this chart UI. We can always do that because of compactness, right? So then what you do, you just pull back this form to a one form over this section, and you integrate it over that section. So that's our definition. Then we find integral of omega over C is equal to sum integral of now C star of omega from Ti minus 1 to Ti, I from 1 to N, where C star of omega is just a pullback of this form. When you have a form over here, we know that there's this pullback operation I define, and then you just define a one form here, you integrate this one form over.
You mean the image of the holomorphism that sends UI to the complex plane?
Oh, sorry?
You mean the chart that sends UI to the complex plane?
No. The chart is just I use only its opens.
Okay.
I don't use coordinates for charts, but I use the map C to pull back the thing.
Okay.
right? So this is the pullback of omega. With respect to C. Because I want to say that I'm on the curve. I'm integrating over. Okay, so that's the definition. And there's a little bit of issue about well-definedness. You have to check the well-defined. That's not a problem. Check that this is well-defined. I mean, you have to check that because someone may take, you may take 10 divisions, someone else may take 20 divisions. It still works for them. So you have to make sure that they are the same. But this is not, this is elementary, you can check. That's not a problem using basic calculus. So once you have that, then you have this integral. Now, okay, so I will give some examples, but now let me just tell you the most fundamental result about this one calculus. So let me recall. So this fundamental theorem of line integrals. In calculus, which is actually a consequence, immediate consequence of fundamental theorem of calculus. So what is it? It just says that if you have a function, U subset of U subset open in Rn, whose, and if you have a curve, to U, and if you want to integrate this one form df over C, you know what the result is. But df is a sum df dxi. I mean, in calculus, you don't write df, you just write gradient of f, but that's really df. Gradient is the wrong concept for this sort of things we are doing. So this is df. What is this?
F of the terminal minus f of the.
Exactly. F of the endpoints subtracted. So this is basically f of c of 1 minus f of c of 0. I mean, proof fundamental theorem of calculus. It's calculus 101. I changed. That's right. Okay. So this is something that exists, works also over manifolds. Same result. Because our formulation is completely invariant now. I can define differential of a function on a manifold. And in fact, in this case, it's a smooth, it's a Riemann surface, and this same result holds over manifolds. Okay. Now, there is one interesting thing which you can do using integration. That's something like Poincaré lemma. Any questions for me? So we are recalling a little bit of initial parts of the wrong theory. And so so this is Poincaré lemma. Or one forms. Let omega equal to sigma Fi gives I. Again, I prove it in general. One for on U, where U is actually an open disk. Open disk, because everything we want to do is just local. I mean, there's no global result like that, but this is local. So you open disk inside Rn. If the omega equal to 0, then there exists the smooth function f belonging to C infinity of this U such that omega is equal to df. Of course, you see, if omega is df, d of omega is 0, right? That's what. So note, if you have a one form, omega is equal to df, it follows that d of omega is equal to 0. But the converse is not true in general. It's a topological statement. In general, this is wrong. As I gave an example actually last lecture about the puncture disk, puncture plane. I gave an example of a one form, d theta, differential of the angle, which is closed, but is not differential of any function. So in general, wrong, this part. I mean, this not implies correct. the conversion statement is in general wrong. That's what I mean. Okay, so, but the beauty of this Poincaré lemma is that if really you are on a nice domain, namely there is no topology, it's contractible, essentially contractibility is the only thing, then you can always write omega equal to df. Actually, it's true for all P forms, even if they are closed over nice domains, namely contractible domains, then it is always exact implies closed implies exact. So, but I mean, here the proof is easy for the one form case. What should I take for F? We can take F to be the following thing. So this is an open disk. I'm gonna start. I'm gonna assume that the origin is the origin of my disk, because everything by translation, that's not the problem. So if you have a point here, like maybe x, I just define f of x to be equal to integral from 0 to 1 of the following of the following function. So my function is following one form, omega. Okay, so let me put it like integral over c omega. Yes. Okay, where c is this straight line connecting 0 to x. I mean, to see why this is true, so let's prove this. So let's calculate this integral, actually, see, so you want to show, okay, so what is df? Is partial f partial xi dxi, right? So what is partial f partial xi? So that's partial xi integral from over c of omega. So that's equal to partial xi integral from 0 to now. Okay, so I just go to x. I'll just go to x, right? So this curve parameterization C from 0 to 1 to x is of the following for the C of t is equal to tx, t between 1 and 0, right? So this becomes integral 0 to 1. Basically, now omega, what was omega? Omega was was fi dxi, right? So this is equal to fi sum fi of, I just write xt dxi. But I mean, dxi, we know what dxi is. dxi is t, is xit. xidt, sorry. Yes, because xi is just xit and dxi is xidt. I'm using again to a fundamental theorem. I mean, just what is this? You can just use, you can portion, just put it inside. So this is equal to integral 0 to 1 d dxi. I mean, sum again, sorry. D fi. Okay, now I have to be careful about my summation, so I just put J here to be not to use the running index. Okay, so I've got dfi dxj, yes, xt xi et, and this turns out to be equal to exactly omega. I mean, this is fi. So from here, then we get df, we basically the sum df dxi dxi is equal to, yes. Okay, I mean, this is quite elementary, but it's a useful fact that we use time to time.
Is the next highest?
Which one?
In the last row.
No, this is xi because I'm taking derivative of all of them because I'm integrating omega. So, but derivative is respect to xj. Yes. So as a result, all those things are 0 except the jth component, which is the one that. Yeah. Okay, now we need a little bit of integration of differential two forms, but that's also more or less straightforward. But let me just now write it. Any questions or? Okay, so now let me just so integration of two forms. X. So this omega belongs to omega 2 of x. Now you can imagine x is a two-dimensional. I don't even assume there is a Riemann, there's a complex structure. It's just a smooth surface. X is a 2D smooth orientable surface. And this omega maybe has compact support, right? So it's just with compact support, and we want to define this omega over x. So what is that? Okay, so what is the how to define this object. So what do you think we need in order to make sure that this is a well-defined concept? For one forms, there wasn't much, but now it's just two forms. So locally, of course, omega, right? Omega is of the form, because it's two-dimensional f dx by dy, right? So what we can do the following. We cover x by coordinate charts. Ui, finite number, because I mean, I can assume even x is compact. Such that, okay, I mean, these are coordinate charts, that's okay. And then what we do, we just choose a partition of unity. Okay, so this is a little bit of differential geometry jargon, but you bear with me. So I use a partition of unity. Let me tell you what it is. Subordinate to this cover. I.e., so what is a partition of unity? So basically, these are smooth functions, right? From x to r bigger than equal to 0, such that support of fi is inside ui, and the sum I from 1 to n is equal to 1. We can always, I mean, there are general results in topology, I mean, a little bit of smooth analysis that tells you that such things exist. But the beauty of these things is that now we can partition omega into sums of omega i's as a result that each of them have support in one coordinate chart. So this is the trick. So if you multiply them here, you get that omega is equal to omega times 1 is equal to omega times sum of fi is equal to sum of fi omega over I, and this is equal to sum of omega I. Okay. So you just, okay, now what happens is the following. So you have this surface. You covered it by finite number of open sets, such that the support of this function is completely inside the union, and we don't care about the rest. You just take large, big open set for the rest, because omega is 0 on the rest. And then we just write it this one. So now support of omega I is inside ui. And then we play the same game now that we did with respect to curves. Now, in other words, we choose coordinate charts. We pull back the form over Rn or R2 in this case and integrate. So here is the definition then. We define integral of omega over x to be equal to sum integral over phi I of ui of phi I star of omega I from 1 to n, right? So let's see, what does this mean? You see, I mean, here, of course, this ui is inside x, and we just choose this phi I to come to R2. Okay, this is phi I of ui. 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 This is phi I ui, and then we just pull back this two form with respect to this map. This pulls back here, you get a two form here, but this two form here is just of the form, I don't know, this is maybe just gi dx by dy. Right? So because there's a standard coordinate chart on R2, so it's dx by dy. Right? So we just integrate that. I mean, what is this integral, by the way? So let me write it like this, phi I RWI. I mean, in calculus or elementary analysis, you don't care about this dx by dy. You just say you're integrating functions. That's wrong, of course. We cannot integrate functions. We have to integrate forms. That's functorially wrong. So you just say gi over phi I of ui. Okay. Now there are two things. Is that once we have to make sure that this is well defined. Two is we have to understand the role of orientation. I mean, we didn't use orientability at all so far. And now I'm going to say that in order to make sure that this is well defined, we need orientability. Okay? So what is that? And all of this is a result of one theorem that, you know, a great mathematician proved in early 19th century. That was his first mathematical paper. What was that mathematician? Who was that? That was his first paper. Huh? His name starts with J.
Jordan?
It was before Jordan.
Oh, no, yeah, Jordan's older, yeah. Jacobi.
It was Jacobi, yes. It was Jacobi, yes. So, and then we need Jacobi's change of variable formula. That's all we need. And let's see what does that say in a little bit of modern language. Jacobi's change of variable formula. So one and two both follow from Jacobi change of variable formula. It has a beautiful geometric interpretation in terms of form that's absolutely transparent. Let me tell you what it is, and then I'll tell you where this is needed. The way, okay. So basically, the result is the following. Let phi from U subset of, in fact, I can just write it over Rn open to phi of U instead of Rn. A diffeomorphism. Diffeomorphism means that it's smooth and it's a smoothly invertible. So this is a derivative is invertible everywhere, right? Okay, so then let omega belong to omega n of phi of u, smooth n form on the domain.
Sorry, did you say that its derivative is invertible or the function is invertible itself?
The function is invertible. Derivatives are pointwise invertible because what is the derivative? Derivative is a linear map from the tangent space to tangent space, and that matrix, Jacobian matrix, is invertible.
So the derivative is locally invertible? You're
What
saying?
do you mean? No, the derivative is just pointwise. At each point is invertible.
Okay. Hmm.
You know partial derivative dfi dxj, the matrix of partial derivatives?
Yes.
That has determinant different from zero at all points.
Okay.
Okay?
Thanks.
So let omega be there, then the theorem is the following. Integral phi star of omega over u is equal to integral omega over phi. Isn't that beautiful? To write it like that? I mean, you can never forget this. Because you pull back, you integrate. So this is invariance of integration with respect to diffeomorphisms. However, you should not work with functions again. You should work with n forms. And when you work with n forms, then if you put functions here, you completely lose track of things. And we said integration is not for functions, it's for forms. If you have a p form, you integrate over p cycles in general, but this is okay, this is in n forms. Okay, the way that you have seen it, I'm pretty sure is something else in calculus. What is it? What you have seen? You have seen the following integral of what? Absolute value of determinant of Jacobian of phi, right? F of, I believe, phi over u is equal to integral of f of x. Okay, so here maybe, I don't know, maybe the n of y is equal to the n of x. Ah, yes. Over u. You see, but I mean, this Jacobian is always confusing. So, but by Jacobian today, I mean the I mean this d phi I dxj, partial derivative matrix. I mean, sometimes people take the determinant of this as the Jacobian. That's also. So for now, let's take that. Okay. Now, the important thing is that there is an absolute value sign here. But in the definition of n form, there is no absolute value sign. So it means that to use my definition, I have to choose coordinate changes that are orientable, that determinant is positive. If you don't choose orientable coordinate charts, coordinate transformations, then everything destroys. I mean, the other part is also follows easily. So, okay, I mean, this is really this term here. The only thing is this absolute value sign. I mean, I have to be able to take it out. You can take it out if this is positive. And to be positive means your manifold has to be orientable. That's it. Okay, so I don't know, this is something you have to think about it also. I cannot say more. By saying more and more, you don't learn necessarily. So you have to think. Okay, I think with that, I'm now, I'll just write the Stokes formula and then we will any questions, by the way? It's better to ask questions. Any questions? Okay, so let me then finish by writing the Stokes formula because that will be our main tool to do other things. Okay, so what's the best way to say this? So Stokes formula. Is it Stokes S with a Stokes or is it? Is it no? Is this Obstrov S? I'm not sure which one is correct. Mr. Stokes.
I think it's just one apostrophe after that.
Yeah.
No, it's not a Stoke. Is it Stoke?
No, no.
No, it's a Stokes.
Yeah.
The last name starts with S. Okay, I emphasize. Stokes. Okay, no, okay, so yeah, this is it. Yeah. S Obstrov, not Obstrov S. It's not Obstrov S.
Only one.
It's no, it's only no, it's a question of commutation. Obstrov S or S Obstrov? It's S Obstrov, yeah. Stokes is yeah. Okay, he was a great mathematician, so he was many Stokes. Stokes formula. I hope this is correct, but you will check. Yeah. So what's the best way to say that? Because there is a lot of things about the boundary of domains. How do I say this? Oh, okay, so let me do two-dimensional version then. So let X be a smooth surface. I mean, this is true in n dimensions, but I just need X be a smooth surface and a subset of X, a compact set with piecewise smooth boundary. Boundary, then let omega belong to omega 1 of X, smooth one form, then double integral. I don't know if I use double integral notation. No, I just say integral of d omega over A is equal to integral of omega over boundary of A. So if you want a feature, this is again the Riemann surface, not the Riemann surface, a two-dimensional surface. So this is A. Okay, this is the boundary of A. You have a one form, you integrate it, no, sorry, you differentiate it, is a two form. If you integrate this two form over this A, domain A, is like integrating the one form over the boundary. This is a consequence of, again, fundamental theorem of calculus. I mean, okay, follows from. Okay, fundamental theorem of calculus. Really, one variable fundamental theorem of calculus. It follows from that, yeah. So this is going to be very important for us because immediately we will prove residue theorem using this, and then lots of other results as we go on. We need this. I mean, this is because I mean, this is fundamental theorem of calculus in the language of forms. So this is something relating. I mean, basically, this shows that this boundary operation in topology is dual, is the adjoint of. This is a relation. I mean, those who like functors should. It shows that D is the adjoint of del, basically. I mean, I can write it like this actually. I mean, as a pair of adjoint functions. So if you look at but this is serious now. This is integral of pairing of d omega A is equal to omega 1 dA. Have you seen the star operation in linear algebra? The star of a matrix, the adjoint of a matrix. You see, you have this like T star xy, for example, equal to x and T star of y. It's exactly like that. In fact, there is a pairing between forms and cycles, and shows that in this world, D is the dual of boundary, and that's what makes. And then you can go on and prove the Rome theorem, Poincaré duality, and all this. So this is a fundamental. This is really fundamental. I mean, but it's completely the same. Or is functor adjoint pair of adjoint non-functors. So any questions? Okay, so this is what we take from calculus, and then we'll just move on. So next lecture we'll go back to complex variables, Riemann surfaces. I don't think I want to say anything because this is just too much now. Okay, so that's enough. Okay. Good.